Let me welcome you to this lecture. We have now seen the kind of point groups that are formed by different combination of symmetry operation, as well as we have also seen how one can systematically determine the point group of a particular molecule, and we are now familiar with this procedure, and we can determine uh, both the symmetry operations that are present within a given molecule, as well as we can determine the point group of the molecule. So now we can use the theorems or principles of mathematical group in solving the problems of chemistry. And for this, first we have to develop a mathematical way to describe the symmetry operations, so that we can use these ways to eventually find out how we can use the group theory to solve problems in chemistry. Now, how one can use mathematics to describe symmetry operations is that one can use matrices to describe symmetry operations, and we will during this lecture we will see how we can use, or what kind of matrices can be used to describe different symmetry operations, or how one can use matrices to perform different symmetry operations. So for this, to begin with, let us have a few important, or let us learn a few important aspects of matrices that are important for us. I am sure you all are familiar with matrices, but some of the things that we need during this course will be discussed now. So matrices, as you all know, is a two-dimensional array of numbers. So it's a matrix which has n rows and m columns. We call it a n by m matrix, or we call the dimension of the matrix to be n by m. Now we can have matrices where the number of rows is equal to number of columns. So that is when we call the matrix as a square matrix. And in group theory, we will be mainly dealing with square matrix, where the number of rows are equal to the number of columns. So then we call, say for example, a matrix, a square matrix which has 2 rows and 2 columns. So we describe the number of rows and number of columns in this way. So we call such a matrix which has 2 rows, or square matrix which has 2 rows and 2 columns, as a two-dimensional matrix. And if you have 3 rows, 3 columns in the matrix, that is a 3 by 3 matrix. We have a 3 by 3 matrix now, so we will call it a 3-dimensional matrix, square matrix. You can also have 1-dimensional matrix. Say for example, this is a matrix which has 1 row and 1 column, so we call this matrix as a 1-dimensional matrix. Now, to describe a particular element in a matrix, you denote its row number as well as the column number. So a ij, I is the I tells you which column row it belongs to, and the number j tells you which column it belongs to. So for example, if you want to describe this particular element which is on the second row and the first column, so you call it the second row. So a 2 1 element is going to be equal to 3 in this case, and similarly a 2 2 is going to be 4, and if you want to know what is a 1 2, that is first row second column, so that is element 2, and say a third row second column is going to be equal to 8. So that is how you describe an element within a matrix by denoting which row number and which column number it belongs to essentially describe a particular element within a given matrix. Also, when you have all the non-diagonal elements within a matrix is equal to 0, that is, so these are the elements for which I is equal to j, and apart from these elements, if all the other elements for which I is not equal to j are 0, then you call such an matrix as diagonal matrix. So elements within a matrix for which I is equal to 0, I is equal to j, that is the number of row is equal to the number of column. Say for this element, its row number is equal to 1 as well as the column number is equal to 1. For this particular element, its row number is equal to 2 and the column number is also equal to 2. And this element, row number is 3 and the column number is also equal to 3. So for these elements, the row number is equal to the column number, and these we call as the diagonal elements for which I is equal to 0, equal to j. And for those elements for which I is not equal to j, we call those elements as non-diagonal elements. And for a square matrix where the non-diagonal elements are all equal to 0, then such a matrix we call as diagonal matrix. Now, for such a diagonal matrix for which all the non-diagonal elements are equal to 0, if the diagonal elements are equal to 1, that is, if you have a matrix the diagonal elements are all equal to 1 while the non-diagonal elements are equal to 0. So this is such a square matrix we call as unit matrix. This is a 3-dimensional unit matrix. We can also write a 2-dimensional unit matrix. This is a 1-dimensional unit matrix for which the only element, which is the diagonal element, is equal to 1. So this is 1-dimensional unit matrix. This is 2-dimensional unit matrix. So now we see different kinds of matrices that are useful for us, or the definition of different matrices that are useful for our purpose here. And now we will also learn about one more important aspect of matrix, that is a transpose of a matrix. That is, you can get transpose of a matrix by converting the rows into columns and the columns into rows. So, for example, if you have a matrix a 3x3 matrix, and so this is equal to A, then the transpose of this matrix is generally expressed as A with superscript capital T. So then you get the transpose by converting the rows into columns. So 1, 2, 3, that is the row, you converted it into a column over here. 4, 5, 6, and 7, 8, 9. So this is the transpose of the matrix A. This allows us to, by doing transpose of a matrix, is going to be very useful for us while dealing with group theory. We will also have to learn how one can do multiply two matrices. That is, in order to be able to multiply two matrices, one condition must be fulfilled. That is, the number of columns in the first matrix must be equal to the number of rows in the second matrix. So, number of columns in first matrix must be equal to the number of rows in second matrix, or otherwise we will not be able to use or do multiplication of these two matrices. So that means what we can do is we can multiply a n by m matrix with a, say, m by l matrix, that is the number of columns in the first matrix is equal to the number of row in the second matrix, and the resulting matrix will have dimension n by l, that is it will have n rows and l columns. So let us now see how one can do matrix multiplication by taking an example of, say, two matrices. Let us take, say, 1, 2, 3, 4 as a matrix, and 5, 6, 7, 8 as the other matrix. So the resulting matrix, to find out the elements of the resulting matrix, what you will have to do is that you have to multiply the elements in both the matrices by you will multiply the elements within a row with the elements of the elements within a row in the first matrix with the elements in the in a column in the second matrix, and the elements, resulting elements will be given by, say, the first element over here. So if I assume this matrix to be A and this to be B and this to be the resulting matrix to be C, then this first element, that is C11, will be given by summation of, say, or let us write it in a more generic way, that is Cij, the element in the ith row and the jth column will be given by summation of all elements in the ith row, product of the elements in the ith row and the jth column in the second row, second matrix, and that will give us the resulting matrix, resulting elements in the resulting elements within the resulting matrix. So let us do this exercise for these two columns. So the first, that is C11, we will get by multiplying the elements in the first row of the first matrix and the first column of the second matrix. That is by multiplying A1k and B1. Sorry. K1. That is, so that will give us, if we do so, that will give us 1 into 5 you will do, and 2 into 7 plus 2 into 7. So this is what will be the first element, the element in the first row, first column in the resulting matrix, and the element in the first row, second column is going to be given by the product of the first row and the second column. So that is 1 into 6 and 2 into 8 plus 2 into 8. Now for the second second row, first column, that is, so we will multiply the elements in the second row and the first column. So that is 3 into 5 plus 4 into 7 will give us, so that is going to be the element in the second row, first column, and the second row, second column element is going to be given by the sum of the product of the elements in the second row, second column. 3 into 6 plus 4 into 8. So these results will essentially give us the resulting matrix by the product of two matrices that we can get. So this is equal to 5 plus 14, and this is 6 plus 16, 15 plus 28, 18 plus 32. So you can get this to be equal to 19, and this is going to be equal to 22. So this is going to be equal to 3 and 3, 43, and this is 0. So this is equal to 50. So this is what we get by multiplying these two matrices. The resulting matrix we could determine by doing the sum of the products of the respective rows with the columns in the second matrix. So that is how one can do the matrix multiplication for different matrices, and this is a very important exercise for our purpose. One more important characteristic of matrices is again important for us, that is the sum of the diagonal elements within a given is called the character of the matrix. So when you do the sum of all the diagonal elements within a given matrix, that is going to be called the character of the matrix, or one also call it as trace of the matrix, either character or as trace. So if you take the matrix, say 3 by 3 matrix of this matrix, and the sum of the diagonal elements is going to be equal to 1 plus 5 plus 9, that is going to be equal to 15. So the character of this matrix, we will call it to be equal to 15. So character we will generally denote by using the symbol chi. So chi is going to be equal to 15 for this particular matrix over here, that we can get by doing the sum of the diagonal elements within the given matrix. So now we are familiar with or most important characteristics or properties of matrix which we need for our purpose while dealing with group theory, and we will now proceed to see how one can use matrices to describe symmetry operations in molecules. So let us now initially try to find out the matrix that we can use to represent the identity operation. So if we take the Cartesian coordinate as the basis now, 3-dimensional Cartesian coordinate, and this is x, y, and z axis over here, and if we assume point with coordinate x, y, z, and if we do the identity operation on this particular point, then the point is not going to move, and its coordinate is going to remain as x, y, z, which is the same as what we have for the initial coordinate. So if we now we can represent the coordinate of this particular point, that is x, y, z, by using a 3 by 1 matrix, that is a unidirectional matrix, we can say, or even a matrix which one of the dimension is equal to 1 are essentially describe a vector, and this particular point, we can use a vector also to describe this particular point, and it can be represented, the vector as well as the coordinate of this point can be represented by this 3 by 1 matrix over here. So that is because it's one of the dimension, that is number of columns in this particular matrix is equal to 1, and that is why it essentially represents a vector. So now when we do the identity operation on the coordinates here over here, or on this vector over here, then the vector or the coordinate of the point do not change. It remains as x, y, and z. So we should now figure out what is going to be the matrix we can use instead of identity operation to, so that when we multiply this we matrix for identity operation with this 3 by 1 matrix for the describing the vector, then we get the vector back as the result. So if you look carefully, what you will find is that we can use the unit matrix, that is a 3-dimensional unit matrix, and when you multiply the 3-dimensional unit matrix with this matrix over here, you will find that the result is going to be equal to x, y, z, because when we do, let us multiply this matrix with this 3 by 3 matrix with this 3 by 1 matrix. So the first product is going to be 1 into x plus 0 into y plus 0 into z. And there is no other column, so it is going to, what we are going to get is going to be equal a 3 by 1 matrix result is going to be the result. So that is the second element that we are going to get is 0 into x, 1 into y, and 0 into z. The third element that we are going to get is over here 0 into x plus 0 into y plus 1 into z. So what you can see, these elements are all going to be equal to 0, and only elements that are going to be left over here is going to be equal to, so that is going to be equal to x, y, and z. So we get the initial coordinates back when we multiply this unit matrix with x, y, z over here, and the result is this. So we can represent the identity operation by using this unit matrix. So when we take what we should notice over here is that when we take the 3-dimensional Cartesian coordinate as the basis, then the matrix representation for identity operation is a 3-dimensional unit matrix. Now if you assume only 2 dimensions, or if you take only 2 dimensions as the basis, that is x and y only, and the point will now have coordinate x and y only, and in that case the identity operation on x and y will give us x and y, and this matrix over here. So the matrix for the identity operation, we will have to write it as a 2-dimensional unit matrix like this, 1 0 0 1. So simply if you take only one axis as the basis, then if you take only one axis as the uh, basis, then you can imagine that the matrix representative of the identity operation is going to be this one, a 1 by 1 matrix whose only element is equal to 1. So you see, when what we have learned over here is that the dimension of the matrix essentially will depend on the dimension of our basis or reference coordinate system actually. When we take the three-dimensional Cartesian coordinate system as the basis, we get the three-dimensional unit matrix is going to be the symmetry of the matrix representation for the identity operation. And when we take the two-dimensional Cartesian coordinate as the basis, the matrix representation for the identity operation is essentially a two-dimensional unit matrix. So the matrix essentially that is going to represent a particular symmetry operation depends on the basis. The basis is very important for our purpose. So let us stick to these three-dimensional Cartesian coordinates and then reduce these matrix representations for other symmetry operations as well. So now next symmetry operation that for which we will try to identify what is the matrix representation is the rotation. Rotation with respect to an proper axis of symmetry. That's right, proper axis of symmetry. So when we do rotation with respect to a proper axis of symmetry, we assume that the principal axis or the proper axis of symmetry of highest order is along the direction of the z-axis, and that is why when we do say in this particular Cartesian coordinate system, you assume the principal axis Cn to be along the direction of Cn, along the direction of z-axis, then the z coordinates. When you do rotation with respect to the z-axis, the z coordinate is not going to change when you do rotation or by any angle. The coordinate of the z coordinate is going to remain essentially same, and only coordinate of x and y coordinates are only going to change. So that means when we do rotation, we do not know by any angle theta say what happens to x and y coordinates, but we know for sure that the z coordinate remains same, z remains z. So the matrix that we will have that represents a rotation with respect to a proper axis of symmetry, that is Cn m, say, essentially we can write is going to be the three-dimensional matrices. We do not know what are the elements over here, but we know for sure that these elements must be equal, these two must be equal to 0, and these two also must be equal to 0, and this is equal to 1, so that the z coordinate do not change when we do rotation with respect to Cn, because the Cn is along the z-axis. So that is for sure that these elements we could immediately deduce, and we do not know what are going to be these elements over here. So because we do not know the final coordinates of x and y after doing the rotation. So we will see how we can find out the final coordinates of x and y when we do rotation by an angle say theta. So let us assume, because now we know that the z coordinate is not going to change, let us only look at x and y coordinates. x when we do rotation with by an angle theta. So let's write this to be an x, the x-axis, and this to be y-axis, and the coordinate, initial coordinate of the point, say is described by a vector r, which is equal to x1, y1. And after we do rotation with respect to z-axis, now z-axis has to be perpendicular to the plane of the board over here. If we assume x and y axis to lie on the plane of the board, then z axis will be perpendicular to the plane of the board, and that is why when we do rotation of the vector r with respect to z axis, it is going to lie on the final resulting vector will lie on the again xy plane, and it will move. Say if we do rotation by an angle theta, so this is going to be equal to theta. So the vector has moved by an angle theta. So this is the final vector, and the final coordinates of the vector is equal to x2 and y2. So we should know the final coordinates with respect to the initial coordinates, and then we can tell what is going to be the resulting matrix or the matrix for a proper axis of rotation with respect to a proper axis of symmetry. So let us try to deduce that by using trigonometry, and let us assume this angle to be equal to alpha, and this angle, of course, with the angle that we have rotated while doing Cn operation, is equal to theta. So then we can draw two right angle triangles like this way, and now by using the simple relation that sine theta is equal to perpendicular by base, and cos theta is equal to perpendicular of hypotenuse b by h, and cos theta is equal to b by h. What we can write here, b P is nothing but your y coordinate, so this is y1, and h is nothing but your vector, that is r. So similarly, cos theta, b is equal to the x coordinate over here, so which is equal to x1, and h is equal to r. So from these two expressions over here, what we can write, from this one we can write that y1 is equal to r sine theta, and from this one over here we can write that x1 is equal to r, not theta, this is not going to be equal to theta, because this angle is equal to alpha, so it is alpha, and this is also equal to alpha. So y1 is equal to r sine alpha, while x1 is equal to r cos alpha. So now let us see what are the final coordinates, again using the same trigonometric rules, that is sine, or say, let us write cos first. Cos theta plus alpha is the final angle for this particular right angle triangle over here. This angle is going to be equal to theta plus alpha is going to be equal to b, that is x2. Base of this triangle is equal to x2, and h is equal to r. So, and also sine theta plus alpha is going to be equal to the perpendicular, that is y2 by r. So from here what we can write is that x2 is equal to r cos theta plus alpha. So what we can write from here is cos theta plus alpha. If we expand, what we will get, cos theta cos alpha minus sin theta sin alpha. So this is going to be r cos alpha cos theta minus r sin alpha sin theta, we can write like this. Now these we know, r cos alpha is equal to x1 cos theta, and r sin alpha is equal to y1 sin theta. So we get the coordinate x2 the function of say x1, the initial coordinate, that is x1 and y1. So we can write this, that is x2 is equal to this. So we will now see what is y2 is equal to. So if you take this particular expression over here, then y2 will be equal to r sine theta plus alpha. So y2 is equal to r, if we expand sine theta plus alpha, so that is sine theta cos alpha plus cos theta sin alpha. This is what we are going to get. So r cos alpha, I'm writing cos alpha before because we want to essentially write it in terms of x1 or y1 plus r sin alpha cos theta. So that will give us, if we convert r cos alpha into x1, so instead of this we can write x1 and r sin alpha as equal to y1 over here. So what we have is that y2 is equal to x1 sin theta, y1 cos theta. So now we know that when we do the rotation by angle theta, this is what happens to the final coordinates of the point we know in terms of x1 and y1. So if we have to write, we know what happens to x1 and y1. So what we will write, or let us leave this and do this only for x and y coordinates. Let us write the matrix representation only for x and y coordinates, that is x and y. When we do Cn operation by angle, when we rotate it by angle theta, what we had is x1, y1 became x1, x2 and y2. So x2 is equal to x1 cos theta minus y1 sin theta, and y2 is equal to x1 sin theta and plus y1 cos theta. So this is the resulting matrix that we get when we do Cn operation or rotate it with respect to z-axis by angle theta on x1 and y1. This is what happens to, these are the final coordinates of x1 and y1. So the matrix for Cn operation, or the two-dimensional matrix for Cn operation, we can write now to be equal to cos theta minus sin theta and sin theta plus cos theta. So this is what is the matrix we can write for over here. In place of for these elements over here, we can write this matrix, and then we will get the matrix for the Cn operation when we do rotation by angle theta with respect to z-axis, which is perpendicular to x and y. Now, if you notice over here, we did rotation in the anti-clockwise direction. So the vector moved from here to here in this direction, but as such, we will do conventionally rotation in clockwise direction. That is, we will do in this direction. So we'll have to do rotation in which is, that is going to be we have to write minus theta in place of theta, and if we write minus theta in place of theta, what we will get minus theta. So cos minus theta is equal to cos theta, we know, and sin minus theta is equal to minus sin theta. So when we do for clockwise rotation, when we write the matrix, this is going to be equal to, for clockwise rotation, cos minus theta, so cos theta it will remain, sin minus theta, this will become minus sin theta, there is a minus sign in front of it already, So this is going to be plus sine theta. This is sine minus theta will give us minus sine theta, and this is cos minus theta will give us cos theta. So this is going to be the two-dimensional matrix for rotation by an angle theta. So this is what we are going to write over here. So the final matrix for the Cn operation, rotation by an angle theta is going to be equal to cos theta sin theta 0 minus sin theta cos theta 0, 0, 0, 1. So that is how we have derived now the matrix representation for a rotation with respect to a proper axis of symmetry by an angle theta. So the matrix, this is a generic form of the matrix. You can put the theta value and then get the matrix for a certain rotation. Say for example, if you do a C3-1 operation where the theta is equal to 120, so you will put theta equal to 120 for each of these cases, and you will evaluate what is the value of cos 120, which is equal to minus half, and sine 120, and that will give essentially the matrix for a C3-1 operation. So that is how we deduce the symmetry operation for different rotation with respect to a proper axis of symmetry. So now let us go and deduce the matrix representation for a reflection operation with respect to a plane of symmetry. So when you take the Cartesian coordinate system x, y, and z, and if your plane of symmetry lies on one of the coordinate planes, that is, if we have to write the matrix representation for say xy, sigma xy, if the plane of symmetry lies on the xy plane, we denote it as sigma xy plane, then we know that the coordinates on x-axis and y-axis are not going to change, but only the z coordinate is going to change. So the matrix representation for sigma xy is going to be x and y coordinate will not change. So 1, 0, 0, 0, 1, 0, 0, 0, minus 1, because z goes to minus z when you do a reflection with respect to xy plane, which is perpendicular to the plane of this board. So z will go to minus z, while x and y will remain where they are. So then similarly, sigma xz, if you want to write, it is very easy to write. So 1, 0, 0, 0, minus 1, because xz plane lies on the plane of the board, y coordinate will go to minus y, x and z coordinate will remain same, so that is why the matrix is going to be this one. Similarly, sigma yz, only the z coordinate is going to change, y and z are, only the x coordinate is going to change, y and z coordinate remain same, and that is very easy to write. So, but the problem is when your plane of symmetry do not really lie on one of these coordinate planes, then it is difficult to write, or one cannot use such simplified procedure to write the matrix representation for such planes. So, for example, if you take the ammonia molecule now, if you assume the C3 axis, again, say the nitrogen atom, and this hydrogen atom lies on the plane of this board, then the C3 axis will also lie on the plane of the board, and this particular hydrogen atom lies on xz plane. If this is the z axis, this is the x axis, y axis is perpendicular to the plane of the board, then this hydrogen atom lies on the plane of the board, and we can write the sigma v, which contains this hydrogen and this nitrogen atom, by using sigma, the matrix representation for this sigma v is going to be this sigma xz. But these two plane of symmetry, as you can see, do not lie on the Cartesian planes, because the y-axis is over here, and this is somewhere pointing over here, which is not exactly on the YZ plane, and similarly this hydrogen atom also do not lie on the one of the coordinate plane, and we cannot use such simplified procedure to write the matrix representation for these two plane of symmetry when we have such molecules. So we need a generic formula to write the matrix representation for such molecules where the plane of symmetries do not really lie on the coordinate planes. So let us again do the same exercise that what we did in case of the rotational while finding out the matrix representation uh, for a rotation operation. And let us now again do, say, let us have a, this is x, this is z, and this is y axis. And when we have a point somewhere over here, say x, y, and z, and let's assume we have now a plane which is a vertical plane of symmetry, because for the horizontal plane of symmetry it is going to lie on the xy plane and we can write the matrix representation. The only issue we have is to write matrix representation for vertical planes of symmetry which are not lying on the one of the coordinate planes. So let's assume that there is a plane of symmetry which is at an angle, say, beta from the x-axis or xz plane over here, somewhere over here, say. So for that particular plane of symmetry, we have to write a matrix representation, say, and to do this again, to simplify this, what we will do, because we know when we do reflection with respect to a vertical plane of symmetry, again the z coordinate is not going to change, because when we, say for example, when you did reflection on xz plane, if you remember, the z coordinate did not change. X coordinate also did not change because the plane lied on the x plane, x axis as well. But now the plane is lying on, it contains the z axis, but it does not contain the other coordinate axis, and that is why the z coordinate is not going to change even when we do reflection with respect to any of these vertical plane of symmetry, which is not lying on the one of the coordinate planes. So that is why again what we will do is we will consider only x and y coordinates which are going to change when you do reflection on one of the vertical plane of symmetry. So let us again write the two-dimensional Cartesian coordinate system. So this is the x coordinate, this is the y coordinate. So the z coordinate now is lying perpendicular to the plane of the board, and the vertical plane of symmetry is also lying perpendicular to the plane of the board. So let us assume that this is the vertical plane of symmetry that we are, for which we want to find out the matrix representation. Now this is the vector that we reference vector for which x1, y1 and x1, y1 is blue. For us, only two coordinates are required. Z is going to remain z because x1, y1. So the final, after we do reflection with respect to the this plane, we see that the vector is going to move, will get reflected towards this side of the plane, and the final coordinate is x2, y2. So x2, y2. So now what we have to do is, let's assume that this plane of symmetry that we have considered makes an angle beta with the x-axis. So the angle it makes, the plane of symmetry makes with x-axis is equal to beta. And let us assume also that this angle between this vector, initial vector, and the x-axis over here is equal to alpha. So then, in that case, this angle over here is going to be equal to because this is going to be equal to, this is alpha and this is beta. So this angle is equal to beta minus alpha. So this is also equal to beta minus alpha. So this angle between, because after we do reflection, we have found it will move by an equal angle from the plane of symmetry. So if this particular angle is equal to beta minus alpha over here between the initial coordinate and the initial vector and the plane of symmetry is equal to beta minus alpha, we have found, because we have assumed that the angle between the x-axis and the plane of symmetry is equal to beta, and the angle between the initial vector and the x-axis is equal to alpha. So this angle is equal to beta minus alpha, we see, and that is why this particular angle as well, that is the angle between the plane of symmetry and the final vector, is also going to be equal to beta minus alpha. So now what we will do is we will write again draw a right angle triangle over here, and what we can write is that, like we have done earlier, that is r x1 is equal to r cos alpha, because alpha is the angle over here, and y1 is equal to r sine alpha. We can write that. So then we will consider now a right angle triangle from the final vector over here and the x-axis over here, so that then we will get x2 will be equal to cos the total angle from here to over here. So this angle up to the plane of symmetry from here is equal to beta, and from the plane of symmetry to the final vector is equal to beta minus alpha. So this is what is the total angle, and that is equal to cos 2 beta minus alpha. So x2 is equal to cos 2 beta minus alpha. So if we, r is going to be there, because r is this hypotenuse is equal to r. So that is why here also we'll have to write r cos beta plus beta minus alpha. So that is, this is also r is going to be there. So that is r, if we expand this, cos 2 beta cos alpha plus sine, because this is cos a minus b, sine 2 beta sine alpha. So that is what we will have. So r cos alpha cos 2 beta plus r sine alpha sine 2 beta. So r cos alpha is x1 cos 2 beta plus y1 sine 2 beta. So this is what x2 is equal to. So x2 we can write is equal to x1 cos 2 beta plus y1 sine 2 beta. So let us now write what y2 is equal to. Y2 will be equal to r sine 2 beta minus alpha, because the angle is 2 beta minus alpha. We have seen earlier already total angle from this vector to x-axis, the opposite right angle triangle that we draw with the x-axis is equal to, so y2 is going to be equal to this. So r, if we expand sine a minus b, now sine 2 beta cos alpha plus, it is going to be or minus, or sine it is going to be equal to minus cos 2 beta sine alpha. So that is equal to r cos alpha sine 2 beta minus r sine alpha cos 2 beta, which is equal to x1 sine 2 beta minus y1 cos 2 beta. So we have the final coordinates, that is y2 we found x1 sin 2 beta minus y1 cos 2 beta. So we have the final coordinates with respect to the initial coordinates, and we know now what happens to the coordinates once we do the reflection operation with respect to a plane which makes an angle beta with the x-axis. So the final matrix that we can write for a reflection operation with respect to a plane of symmetry which makes an angle beta with the x-axis is going to be equal to cos 2 beta sin 2 beta 0, that is sin 2 beta minus cos 2 beta 0 0 0 1. So that is what the reflection matrix representation for a reflection theta with x-axis. So we can deduce the angle that is that the plane of symmetry makes with x-axis, and accordingly we can derive the matrix representation for the particular reflection operation for a certain plane of symmetry. So now we with this we will conclude this lecture. We have essentially seen how one can use matrix algebra in determining different, in deducing in representing symmetry operations. That is, we have deduced the matrix representations for different symmetry operations. That is, identity operation we have done. We have also done rotation with respect to an axis of symmetry, and we have also done reflection with respect to a plane of symmetry, and we have deduced or derived the generic matrix representations for all these symmetry operations. Now, the rotation with respect to an improper axis of symmetry is left, so we will deduce the matrix representation for rotation with respect to an improper axis of symmetry in the next lecture, and then we will see what we can do with these matrix representations. So with this, then we conclude this lecture. Thank you very much for being with me during this lecture.